Hello, this is lecture 5, stat 134. Last time we talked about the mode of the binomial distribution. Remember, the mode is the floor of np plus p, unless np plus p is an integer, in which case m minus 1 and m are the mode. Remember, the floor is the integer part of a number, so the floor of 7.2 is 7. So for example, if n is 10 and p is a third, the mode is the floor of np plus p, which is the floor of 3 2/3. 3 2/3 is not an integer, so we have a single mode, namely 3. So today we're going to finish 2.1 and start on the normal approximation to the binomial. So here's an example. For each n, what's the smallest value of p such that n is the most likely number of successes? So let's take a look at that in an example. So say that n is 3. So what's the smallest p such that 3 is the mode? So we see that when p is 7/8, 3 is the mode, and when p is 3/4, 3 shares the mode with 2, but that's it. 3 is still the mode. But if you're any bit less, if p is any less than 3/4, then 3 will no longer be the mode. So in other words, we need np plus p to be between n, including n, and n plus 1. In particular, when np plus p is exactly n, then we have n and n minus 1 being the mode, and any smaller p will result in n not being the mode anymore. So we just need to solve the equation n equals np plus p for n, so p is n over n plus 1. Now the mode is a measure of the center of your data. The true center of your data, however, is the expectation or mean. Now, here's a fact shown in chapter 3 that the expected mean number of successes is mu equals np. Now, this isn't usually an integer. For example, when n is 5 and p is a half, mu is 5/2. So I can show that right here. Now, if the mean is an integer, it is true that the mean is the mode, because if np is an integer, then np plus p, the floor of that, is np, and np plus p is just a little bit more than np, so the floor of that is np, and np is an integer, so the mean is the mode. Now, another fact to be shown in chapter 3 is that the average spread around the mean, or the standard deviation, is sigma equals the square root of npq, where q is 1 minus p. So notice that the spread around the mean gets larger as n gets bigger, because n is in the numerator here. You can see an example for the binomial n1/2 that as n increases, your histogram gets more spread out. So then we did a concept test. A fair coin is tossed and you win $1 if there's exactly 50% heads. Which is better, 10 tosses or 100 tosses? So the answer is A, because as n increases, the spread increases and the probabilities go down. So for example, probability of 5 is actually 0.246, and the probability of 50 is 0.08. Now some of you said B, and cited the law of large numbers, but the law of large numbers is about the proportion of successes, not about the number of successes. So does not apply. The proportion of successes, or I should say the spread of the proportion of successes, does go down as n increases. Now, the normal approximation is the subject of section 2.2. The motivation is that it's difficult to calculate exact probabilities with the binomial formula, much easier to calculate the area under the normal curve. So here you have, for example, a situation where, let's say you wanted to know what's the chance of having between A and B number of successes, it'd be much easier to calculate the area under the normal curve between a little bit less than A and a little bit more than B. That's called a continuity correction. We'll get to that in a minute. But let's first talk about the normal curve. So the normal curve is given by this exponential equation here. It has some properties. It has two parameters, the mean and the standard deviation. It has inflection points at mu and plus or minus sigma, and almost all the data is within 3 SDs of the mean. So to find the area under this curve, it's convenient to make a change of variables, and z is x minus mu over sigma, and that has the effect of making mu 0 and sigma 1. That gives us the standard normal curve, whose density function is given here. And we can define the cumulative distribution function, which is the area between minus infinity and z. And its graph is a sigmoidal shaped running from between 0 and 1. You can't solve the CDF exactly. Rather, you need a lookup table or computer to find it. So you can use, for example, the normal table given in the book here. So to read this table, if you wanted to find phi of 1.00, you'd locate 1.0 row in the row and the second decimal in the column, and you'd see that phi of 1 is 0.8413. Now notice that the z's given here are all greater than or equal to 0. So how are you going to use this if you have a z that's negative? Well, here we can rely on the fact that the normal curve is symmetric, and so phi of minus z is 1 minus phi of z. So we can find the area between 1 and minus 1 to be 0.68, and so on. This gives you the empirical rule, which says that 68% of your data lies within 1 SD, 95% of your data within 2, and 99.7% of your data within 3. Now, the normal approximation to the binomial distribution leads us to two questions. How are we going to match the normal curve with the binomial? And the answer is that mu is NP and sigma is square root of NPQ. The second question is, when is it appropriate to do this? So we can see from this table here that for a given p, that is n increases, the distribution looks more normal. That's a result of the central limit theorem that we'll see in chapter 4. But still we have problems when p is close to 0 or close to 1. So when that happens, we have to be careful. So what we do need is, let's require that n be greater than 20 so that our binomial looks more normal. And furthermore, let's require that our data be between mu plus or minus 3 sigma. So we have a picture like this, right? Because our outcomes are between 0 and n. So this is going to require that mu minus 3 sigma be greater than 0 and mu plus 3 sigma be less than n. So with that requirement, we should be good. So for example, if n is 20 and p is 1/10, then mu is 2 and sigma is 1.34, so 3 sigma is equal to 4. And 2 minus 3 sigma is minus 2, which is less than 0. So this won't be good because the binomial distribution will look like what we have in the picture here. It'll be cut off at 0. So to make a normal approximation to the binomial, we want to use this formula here. And this is, again, motivated by this picture where we don't want to take the area under the normal curve between A and B, but rather a little bit less than A and a little bit greater than B. So we want to take A minus a half because the block width is always 1, and A, the integer A, is in the middle of that block. So we have a half on either side of the integer. So we actually want the area, to find the area from A minus 1/2, and on the other side B plus 1/2, and then we normalize by subtracting mu and dividing by sigma. So for example, to find the approximate chance of getting 75 sixes in 600 rolls, we let A equal B be 75, and then look at phi of 75.5 minus 100 over 9.1, and 74.5 minus 100 divided by 9.1, which is 0.00101. You can, of course, calculate it exactly using the binomial formula.